Okay, so how the CPU execute? The program always start at main function and finish the last instruction as return. Okay, so this is the last instruction to return. Return to the caller function. Okay, return to the caller function. And the numbers inside the registers are numbers assigned to complement. Okay, the numbers inside the registers are assigned to complement. That's why you need to learn chapter 4. Okay, plus the floating point numbers. I'm not going to explain this loop because it's a little bit in chapter 5, but you need to understand that the execution starts from here, and then here, and then here, and then here. Okay? There, here, here. No. Until here, it checks for the greater than condition, and the loop happens because R1 is greater than 0. That's what GT stands for, greater than. And the condition is true, then it's looping again and again until R1 becomes 0. Because R1 gets subtracted by 1 every loop. Okay? Until R1 becomes 0, then it's going to execute the next instruction and the next and the last to return. Okay? If you recognize LR, that's R14. Okay? So to return in C, you normally return with an integer number. Why? Why we return an integer number? Because we declare main as an int function. We declare main as an int function. So int means you need to return some integer number. Okay? That's what happened in lab 6. What happened in lab 6 is I borrow some of your lab 6 okay, I don't tell you who's this lab 6 exercise 4. This is correct. Okay? Because the exercise told you to start from -1 and keeps looping until I become greater than 0. I become positive. Okay? So I start from -1 all the way to -2 billion something. And then once you subtract more to -1 to I, it's going to become positive number, which is 2 billion something again. Okay? And this number corresponds to 2 to the power 31 subtract 1. This number corresponds to 2 to minus 2 to the power of 31 alone. Subtract 0. Okay? This one all together you have 2 to the 32 permutations. Remember, permutations. Because an int is 32 bits long. An integer is 32 bits long. Okay? That's why you get 2000 billion for the positive side, another 2000 billion for the negative sides. Okay? Just like what? Just like this figure. Okay? Because this is the boundary. We keep subtracting from minus 1 to minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. And then when you subtract one more, you cross the boundary. This is the boundary to become positive number. This is the negative part. Okay? That's why this circle line number is so important. Because I cannot draw a circle of 2 billion or 4 billion numbers. I can draw only 4-bit number for you. Okay? If you happen to change this to be 32-bit, the boundary is going to be minus 2 billion and plus 2 billion something. Okay? And if you keep subtracting one more, what happened? Subtract one more, you're going to cross from the positive side to the negative side again. Okay? But how long it's going to take? In this figure, only from minus 1 to 2 billion, it took 9.7 seconds. Okay? But again, the CPU is so fast. If you happen to do this in Raspberry Pi 3, it's going to be 20 something seconds. It's much longer. It's going to take longer time. Because Raspberry Pi 3 is slower than Pi 4. Okay? Are we clear now? What happened? So if your answer is a little bit different from here, you get deducted by 0.2 or 0.3 points. Okay? Don't worry. Because I want you to really understand the report, the output. It's not that important. If you can create a source code like this, it's good enough. Okay? Okay.